Hi friends, let us learn today another algorithms called Kruskal'S algorithms. Kruskal'S. This is also to find minimal spanning trees, minimal cost spanning trees, right? And for this, again we are using the greedy method. Remember that greedy method? What I said? We are finding the possibilities, all feasible solutions based on the given constraints, and out of that feasible solutions, we are going to find an optimal solutions. So here in Kruskal, we'll be having different approach. Prim's algorithm, we have decided about the source vertex, and then we start traversing it, right, and finding that optimal solutions. And you can say that sum of minimal spanning tree edge. So it should be minimal cost spanning trees. So let us see that what is Kruskal's algorithms, and I believe everyone is aware of spanning trees. We have discussed in details what is spanning trees, friend, and how to find minimal spanning trees, right? So again, this spanning tree is a undirected weighted graph. It is a trees called acyclic graph and having v number of vertex, n minus 1 number of edge. If n is a number of vertex, n minus 1 number of edge. Okay, n vertices and n minus 1 edges, and the total cost associated with that spanning tree is called minimal spanning trees. So these all we have discussed in that previous lectures as well. We have seen that how to find out from given graph to minimal cost spanning tree. Okay, we can see that number of vertices is 5, number of edges is 1, 2, 3, 4, 5, 6, 7, 8, right? We will see that there are 8 vertex edges, but in minimal spanning trees number of vertex will be same, but number of edges is 5 minus 1 is equal to 4. So this darkened red color is spanning trees, selected spanning trees, and total cost is minimal cost, because we have many solutions out of it, but 4 plus 2 6 plus 4 10 plus 5 15. Okay, so this is minimal cost. In previous lecture we have discussed that how you are going to find different spanning trees. Remember that there is no limitation of a spanning graph from the given graph. We can have multiple spanning graph. We will have multiple spanning graph. Say as for example, if you are saying this is one of the example. How many number of vertex we have? 1, 2, 3, 4. N is equal to 4. So now this is one example. How many vertex we have? 4. This is another. How many vertex? 4. This is. So we can have multiple spanning trees, friend. We can have multiple spanning trees. Okay, even person can go like this, they can do like this. So these all are the spanning trees for the given example called, we are having 4 vertex and 5 edges. So you can draw multiple spanning trees. Only thing is number of vertex will be same, but number of edges will be 1 less than the number of vertices. So in this particular case, we are having this 4 vertex. Now let us discuss Kruskal's algorithm, and what you have discussed in the previous examples, we'll go and discuss in the similar way, right? And better we can have different examples such a way that we can discuss in details. Remember that here you are not asking from the user source vertex. Say we are having input A, B, C, D, E, F, right? So it is 2, 2, 3, 3, 6, 5, 1, 6, 4, 5. So these all are the which kind of graph, friend? It is called weighted undirected weighted graph. There is no direction on their edge, hence it is undirected graph. Weight is there on edge, hence it is called weighted graph. So, undirected weighted graph. So we required for that Prim's and Kruskal'S. It doesn't mean we cannot perform the task for that directed graph. Yes, we can do it, not a problem. But in undirected graph, we'll be having more possibilities to discuss, while in directed graph, we'll have lesser possibilities to discuss. In Kruskal'S algorithm, what first we are going to do it is, since we don't have any source vertex, and we know that we have to find out the minimal spanning trees. So we are going like as we'll ask from the person who doesn't know the technology also, who doesn't know the method also, and based on their greediness, they can tell. If you're going to say that find out the minimal spanning trees, if they're knowing minimal, or you can say that find the minimum values out of it. So pakka, they will go and select this E to F as a 1, B to C or A to B as a 2 2. They are going to select like this. They are going to perform the task. They will say you that this is the minimum spanning trees. In similar way, we have to make compiler, we have to make computer to understand what we are supposed to do. And what are we going to do? We are going to find out the minimum values on their weight. Minimum values as a weight on their edge. And how are you going to find out? Just identify that values by running that for loop, find the minimum values among this, and if you are going to find the minimum values, it will give you that E to F 5 to 6, E to F is a 1. So we are going to select first E to F, right? So let us see that. What are we going to do it? We have edges. Say we have a remaining edges, right? So what basically we're going to do it here is, first of all, we don't have any vertex, right? We don't have any edges. What you're going to do it is, first you write all these elements in increasing order of their weight. Increasing order of their weight means what? First E to F will come into the picture. E to F. And what is the weight? Is 1. Similarly, what is next? A to B. Just I am writing A comma B as a AB. A to B. This is what? A to B. Okay. A to B is 2. Similarly, B to C is 2. Right. Then what is the next minimum? 1, 2, 2, 3. B to E is 3. Right. C to E is 3. Then C to D is 4. Right. D to E 5. D to F is 5. And A to E is 6. So if you see that we have write down all the edges in increasing order of their weight. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 9. Which is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, yeah. One more we have A to E and A to F is 6. Right? Now, we can see that out of these edge, which is having minimum edge, minimum weight is first one. And what is that values? E to F. So, we are selecting E to F, that one. So, this is already selected. So, remaining edges, we are going to write as it is. AB 2, BC 2, BE 3, CE 3, CD 4, DE 5, DF 5, AE 6, AF 6. So, you have selected AE. E to F you have already selected. Right? Similarly, now next minimum element is 2. So, you are going to select AB 2. So, remaining is BC 2, BE 3, CE 3, CD4, DE5, DF5, AE6, AF6. Out of that, which is minimum? BC is minimum. So AB we have already selected. We can write it this again and again, this graph again and again. AB we have selected. Now next is BC. So BC2. We have selected BC2. Right? Thereafter, we have BE3, CE3, CD4, DE5, DF5, AE6, AF6. So, after that you are going to select B2E, BE3. So, you have selected BE3, right? Look, if I selected that, now CE3, CED4, DE5, DF5, AE6, AF6. Now what is next minimum? Next minimum is C2E. Next minimum is C2E. But look, if you are going to connect C2E, if you are going to connect this C2E, it makes a cycle. But what is our spanning trees? The spanning tree is a cyclic graph. So whenever you are getting cycle, we are going to put cross and say that it's forming cycle. Forming cycle. So this particular CE, C to E is forming cycle. So even though it is lesser values, we are not going to select for the spanning trees. So then C to D. C to D, it's not forming cycle, so let us have C to D outside. C to D. So we have selected this as even though it is greater than 3. That is case we are writing here D2 E5, D2 F5, A2 E6, A2 F6. Let us see that now. We have among this D to E is minimum. If you are connecting D to E, this makes a cycle. This forms cycle. So again you are not going to select this D to E, right? D to F. We are connecting D to F here. So this forms cycle. Look, this forms cycle. So we are not going to select this also. A to E. We are connecting A to E. A to E. So this part is making cycle. If you are making cycle, we are not going to select because this is against of a spanning trees rule. A to F. If I am going to connect A to F like this forms cycle. Hence it is not a spanning trees. So first fundamental thing is we are not going to select any edge that forms cycle. So we are going to reject that. So why we rejected this all is forming cycle. Okay. Hence rejected. Hence rejected. So whatever the edges you have selected in left hand side 1, 2, 3, 4, 5. So how many number of edges you have selected, friend? 5. So these 5 vertex, these 5, 1, 2, 3, 4, 5 edge is called a spanning trees. Right? So we have A to B, B to C, B to E, C to D and E to F. If you will see that cost 2, 2, 3, 4, 1. So total cost of a spanning tree is 2 plus 2 plus 3 plus 4 plus 1. Hence it is 12. The cost of spanning trees. So this is the outcome of Kruskal'S algorithms, and we are finding a spanning trees, a cyclic graph having lesser cost. So what happened, friend? What you make the conclusion over here is in Kruskal'S, first of all you are going to find out the first minimum values among these. First minimum values, it was E to F. Then you are going to find out second minimum values. So first minimum values, a moment you got it, we have to ignore this. If you wanted to ignore this, how will ignore it? We'll put at the place of that particular edge 1 some larger value is infinity. Then you are going to find out next minimum elements again in same loop for I is equal to 1 to 6, j is equal to 1 to 6, and find again next minimum element. So you got this A to B. If it satisfies all the constraints of minimal spanning trees, select it. Then go to the next minimum element. Again, we need to keep track and keep check that that particular age, new age is not forming the cycle. That is the fundamental things. We have to do it. And finally, we'll get that final answer. Okay. So let us see that in Kruskal, what we did it first, friend? Do you remember what we did it first? What did it first here? We have arranged these all age based on their weight in increasing order, right? So same things we are going to check about here is ET, the set of edges composing a minimum spanning trees of G, sort E in non-decreasing order, means increasing order, right, of edge weight W of E1 to W of all last vertex. Then initially when you started with this, we don't have any darken edge. So it means selected for the spanning tree edges was empty. We don't have any edges for spanning trees. So we have defined it ET as a 5. ET as a 5. We don't have any. Now we have one counter counting for number of edge. Counting the number of edge. So again we can see that how many number of edges you are going to get? Number of vertex minus 1. Look, 1, 2, 3, 4, 5. And how many number of vertex you have? 6. 6 minus 1. So it will go to 5 iterations. It will go to 5 iterations. And what you are going to do it basically ET union E of ik if it is acyclic, mark it here, acyclic. If by combining these age to existing age, if it is not forming the cycle, then you are going to select this particular age ik to et and count will increase by count plus 1. And how many number of times you are going to do this? As depends on the number of vertex present in the graph minus 1. So that many number of times you are going to perform this task. At last you are going to get all set of edges, right? So how we are going to write it here? All the set of edges, what you are getting? A to B is 2, B to C is 2, B to E is 3 and C to D is 4 and E to F is 1. So you can start with 1, E to F is 1, A to B is 2, B to C is 2, B to E is 3, C to D is 4. About again summary of this algorithm is it is Kruskal'S algorithm used to find minimal spanning trees. Again, time complexity is E log V, but if you wanted to consider even time taken to sort the element in increasing order, time taken to sort the element in increasing order, for that if you are using merge sort, then your time complexity will leads to n log n base 2, right? Here is E log V, so it is n log n, very close to both. But if you are using some other technique, say bubble sort, right, to sort all the edges at the beginning, then it leads to n square complexity. You know that n square is greater than n log n. So in a standard way, we call it as this is the time complexity of Kruskal'S algorithms, right? And wherever we require pre-sorting technique to sort the element then perform the task, it is always suggested that we can go for the merge sort to keep our time complexity as lesser as possible. So we'll stop the class here. Thank you very much. We'll meet you in the next class.